This is section 10.3 on polar coordinate system. We have a polar coordinate system is a plane with a point O, the pole, and a ray from the pole, or O, the polar axis. Each point P in the plane is assigned polar coordinates as follows. R is the directed distance or magnitude from O to P, and theta is the directed angle whose initial side is on the polar axis and whose terminal side is on the line OP. So imagine you're out in a big field and you want to locate points in this big field. What you could do is, to locate points, you could literally drive a pole right into the ground, and if you had a rope, you could find a point by extending out the rope to that point and then marking it with some sort of angle that you've determined the initial side. So the point 0, 0 for rectangular is called the pole in polar coordinate, because if we extended a rope to, let's say, point A and then assigned it an angle, we could find that unique point. As in trig, we measure theta as positive when moving counterclockwise and negative when moving clockwise. If the radius is greater than 0, then P is on the terminal side of theta. If R is less than 0, then P is on the terminal side of theta plus pi, in other words, in the other direction. So we can use radian or degree measure for the angle theta. So let's say we have this point out here, point A, and we're using rectangular coordinates. So we have the point 1, 2, 3, 4, 1, 2, 3, 4, 5. So A is the point 4, 5 in rectangular coordinates, but we want to locate this point using polar coordinates. Well, we start at the pole and we extend the rope out that far right there. Well, what that represents is a certain radius of a circle. So we could draw that circle out to that point. Now, just having the radius of the circle really wouldn't pinpoint, it wouldn't lock this point down, because if you just gave a radius, the point could be anywhere on the circle. But what really locks this point down is the angle that's given. So if you give a radius and this angle only, then this is the only point that those two could possibly give. Now what this is talking about, if the radius is greater than 0, for example, if we have a radius here, here would be the radius if it was positive. But if you give this same angle and you make R negative, that means you're at this angle, but instead you're going in the opposite direction. So the point would be somewhere over here. This would be negative R. And that's why it says theta plus pi, because you're going in the direction a half a circle away from the angle that's given. Point A can be located by using the Cartesian coordinate system, or we could locate it using a radius and some sort of angle, and we usually talk about the angle being theta. Example 1, plot the points with the given polar coordinates. All right, so the first one has a radius of 2. So we have, here's a radius of 1, here's a circle with a radius of 2, and then we go to pi over 3. So that pi over 3 is about right there. In letter B, we have a radius of negative 2. So I do know that I'm going to have a circle with radius of 2. We go to 3 pi over 4. 3 pi over 4 would be somewhere about right there. There would be the point if 2 was positive, but it's negative, so we go to 3 pi over 4, and then we just go 180 degrees in the other direction. So right there would be negative 2, 3 pi over 4. That's that point right there. In letter C, we have a radius of 3. So there would be a circle of radius 1, radius 2, radius 3, with negative 45 degrees. So here would be negative 45 degrees, and so the point would be somewhere about right there. Each polar coordinate pair determines a unique point. So once you determine an R, excuse me, for example, maybe a radius of 2 and pi over 4, that is a unique point. There's only one point that satisfies those two conditions. However, the polar coordinates of a point P in the plane are not unique, meaning I can mark this same point by using different coordinates. For example, negative 2 comma 5 pi over 4 would give, these two would give the exact same point. One would be, one would have an angle here and the radius of 2. The other one would go, the angle would go all the way pi radians farther, but if I gave the R a negative value, it would end up being the same point. So once we label the coordinates 2 pi over 4, that's a unique point, but the other way around is not unique. The coordinates r theta plus 2n pi, which means go all the way around the circle, and negative r, go halfway around the circle, all name the same point. In general, the point with polar coordinates r theta also has polar coordinates. So if we have this coordinate right here, it would be the same as r and then go all the way around the circle, or negative r and just go halfway around the circle, because this would be an odd number. For example, 2 times 1 plus 3, or 2 times 1 plus 1 would be 3 pi, which would end up being, of course, all the way around, but then halfway around the circle again. Where n is any integer. In particular, the pole has polar coordinates 0 theta, where theta is any angle. So if you have a radius of 0, that puts you right on the origin with any angle that you want. It's still just going to be a point if the radius is 0. In example 2, if the point P has polar coordinates 3 pi over 3, we're going to find 3 additional pairs of polar coordinates for P. So here's the point that we're looking at right there, 3 pi over 3. Well, if we go all the way around the circle, start at that angle, go all the way around, we get to the exact same value. So we would take pi over 3, and we would add 6 pi over 3, which is 2 pi. So I could have the coordinates 3 comma 9, no, excuse me, not 9, 7 pi over 3. That's a 7. Another coordinates that would give the exact same points, I could go negative angle, which would be negative 2/3, negative 3 comma negative 2 pi over 3. That would give the same point because it would put us 180 degrees away from where we need to be, but then if you go backwards with the negative 3, you get back to the same point. A third one I thought we could have would be to go 180 degrees in the opposite direction, in the positive direction. In radians, I always think of radians more than I do degrees. That would be, this would be 3/3, this would be 4/3, so 4 pi over 3, and then we just have to make the radius negative 3, so we'd go backwards, and that would also get us to the same point. Coordinate conversion. When we use both polar coordinates and Cartesian coordinates, the pole is the origin, 0, 0, or polar would be 0 and then any angle you want. It could also be 0. The polar axis is the positive x-axis. By applying trigonometry, we can find equations that relate the polar coordinates r theta and the rectangular coordinates x, y of a point P. Let the point P have polar coordinates r theta and rectangular coordinates x, y. So what this is talking about is we can convert from polar to rectangular and rectangular to polar, and we go back and forth. And we use these tools to do that, and these tools we already know. The x-coordinate is r times the cosine of theta, and the y-coordinate is r times the sine of theta. Now we put r in front of here because we don't necessarily have to be on the unit circle. We can be on a circle of 1, the unit circle, or a radius of anything you want, 2, 3, 5.5, whatever we need. Another relationship we have is r squared, or the radius of the circle, equals x squared plus y squared, and we can also use the tangent of theta equals y over x. These relationships allow us to convert from one coordinate system to the other. In example 3, find the rectangular coordinates of the points with the given polar coordinates. So here's some polar coordinates, and we need to convert to rectangular. And of course, the cosine of 5 pi over 6 is square root of 3 over 2, and sine of 5 pi over 6 is 1/2. So the rectangular coordinates are negative 3 square root of 3 over 2 and 3/2. In B, instead of using radians, we're using degrees, and negative 225 degrees puts us at really what I think of as 3 pi over 4. So here's 3 pi over 4. The coordinates are square root of 2 over 2, negative, and positive square root of 2 over 2. When converting rectangular coordinates to polar coordinates, we must remember that there are infinitely many possible polar coordinate pairs. In exercise 4, we report 2 of the possibilities. In exercise 4, find 2 polar coordinate pairs for the points with given rectangular coordinates. So this is a rectangular coordinate, negative 1, 1. Let's keep in mind that this point is in quadrant 2. We have the relationship that r squared equals x squared plus y squared. In this case, r squared equals 1 plus 1. I squared both the 1's and the negative 1. And we have the radius equals plus or minus the square root of 2. Now, tangent equals y over x. So we have 1 over negative 1, which is negative 1. So theta equals 3 pi over 4. That would put us also in the second coordinate if we use 3 pi over 4. So we have square root of 2, 3 pi over 4. And if I go to 7 pi over 4, which is pi radians around the circle past the 3 pi over 4, and then make the radius negative, square root of 2, we get to the exact same point. And letter B, we have a point that's actually on the x-axis, 3, 0. We use the same relationship. We get the radius to be plus or minus 3. Now, if I use the angle of 0 and the radius of 3, that gets to the point. Or I could use an angle of pi and make the radius negative 3. So instead of going along to pi, we would go in the opposite direction, of course. In exercise 6, we want to convert the rectangular equation to polar form. Now, polar equations look like something like r equals, let's say, sine of theta. Just like in rectangular, it equals y equals x squared plus 3. We have a function with y equals, and then something happens to x. Well, in polar, our equations look like radius equals something having to do with angles. So on letter A, we have x equals 5. Well, x is the same as r cosine of theta, and we saw that back here, x equals r cosine. So instead of x, we can have r cosine. And it equals 5, and then we divide by cosine of theta. So we have what we want, r equals something to do with theta. In letter B, we replace the x with r cosine and the y with r sine, and leaving the 3 and 4, of course. We can factor out an r, and then divide by 3 cosine theta plus sine theta. In letter C, we have a circle with the radius not at 0, 0. The radius is actually at 1 negative, or the center is at 1 negative 4. If you FOIL out x minus y squared, you get x squared minus 2x plus 1. If you FOIL out y plus 4 squared, you get y squared plus 8y plus 16, and that's equal to 17. Well, 16 plus 1 is 17, so we subtract 17, getting 0. That takes the constants away. Now, x squared plus y squared is r squared, so we use that somewhere. Back right here, x squared plus y squared is r squared, so we can make that replacement. X squared plus y squared is r squared, and then x is r cosine, y is r sine. We can factor out an r with all 3 of these, so either r equals 0 or r minus 2 cosine theta plus 8 sine theta equals 0. Well, if we have a radius of 0, all we have is a point. We don't have this curve, so it can't be r equals 0. It's got to be the second one. So we add the 2 cosine over, and we subtract the 8 sine over.